So you are in the talk, Rust, a language for the next 40 years. My name is Carol Nichols or Goulding. It short circuits. I will answer to Nichols quicker, but you can also call me Carol Goulding if you want. I'm Carol's 10 cents on all the various platforms. I have a lot of links in my slides, so if you want to be able to follow up on references and check out some more things, this short link will take you to a repo where there's a link to view the slides on the web, and the README has just the links pulled out. As sort of alluded to in the intro, I'm the co-author of the Rust Programming Language book, which is available for free online and available in print from No Starch Press. I'm also co-author on a Manning live video series called Rust in Motion that's in early access right now. And thanks to Manning, I have 3 codes for free access to this Rust in Motion. So my favorite 3 questions are going to get access to this. So please ask wonderful questions on the Slido question asking platform. I am also a co-founder of Integer32, the world's first Rust consulting company. And I am an organizer of Rust Belt Rust, a regional Rust conference. This year we're going to be in Dayton, Ohio on October 18th and 19th. And I'm on the Rust core team. So if you were hoping for an objective, unbiased look at Rust, you're not going to get that from this talk. I clearly have a slant here. I love Rust so much that my favorite hockey player is 2-time Stanley Cup winning champion Brian Rust from the Pittsburgh Penguins. And yes, you may throw tomatoes at me or batteries or whatever it is that you do here in Philadelphia. I can take it. All right, so in this talk today, we're going to talk a little bit about the railroad industry. Bet you weren't expecting that, but we are. We're going to talk about C, we're going to talk about Rust, and we're going to talk about what the software industry can learn from the railroad industry. So a little railroad industry history. Commercial railroads in the United States started being built around 1830. And trains were really great. They let you get across this huge country of ours a lot faster than things like stagecoaches. And they really took off, built lots of lines of rail all around the country really fast. But as the miles of rail and as the train trips grew, injuries and deaths also grew. It turns out that once you get a big train moving, it's kind of hard to get it to stop again. And there were lots of collisions, there were lots of accidents, and one of the most dangerous jobs on the railroads was that of the brakeman, because the way you used to have to get trains to stop is the engineer would blow a certain signal with the whistle that he wanted to stop, and then people would have to go up on the top of each car and turn this wheel to put the brakes on, and then move to the next car, and eventually the train would slowly come to a stop as all of the brakes were applied. But this wasn't really an exact science, so at best case, if this didn't go well, you would miss the station you were trying to stop at. Worst case, if you needed to stop in a hurry, you probably couldn't, and there were collisions and accidents. And this job, being on top of the train when it was rainy or icy, is pretty dangerous. And a lot of brakemen would fall off the train and be killed. The thousands of brakemen died every year. This is second only to mining as the most dangerous career in the 1800s. Enter George Westinghouse, an amazing Pittsburgher. He invented lots of things, was part of making electricity viable and commercially available. And in 1869, he invented the first air brake. There have been improvements made over the years, but essentially his air brake is what trains use today. The way air brakes work are that they're controlled by compressed air rather than a physical wheel on the top of the car. There's a control up in front for the engineer to turn the brakes on and off so that they don't have to use the whistle to communicate. All the cars are connected so that when the engineer turns the brakes on, all of the cars start braking all at the same time. And a later failsafe was added so that when there isn't pressure to each car through this connection, the brakes are on so that this is safe by default. You would have to apply the pressure to turn the brakes off and get the car moving. So if all this got disconnected, the train would come to a stop instead of continuing to go. And this system was a lot more complex than the handbrakes, and there was some skepticism. This was a quote from Vanderbilt, who was the guy behind Vanderbilt University eventually, but he couldn't believe that error was going to be what stops trains. But they did a lot of public tests, a lot of demonstrations that involved people riding in train cars with like pillows everywhere, testing all these sorts of different kinds of brakes and like running into the walls because when different kinds of brakes didn't work. But the air brakes were passing all these public tests, and they were a lot safer and a lot better at getting the trains to stop than the handbrakes were. Railroads adopted these for passenger trains pretty quickly because consumers demanded it. This is an advertisement for a particular train, and this yellow part here says that the swift operation of these nightly carriers is safeguarded by Westinghouse air brakes. So this was something that the market demanded, that there were people who were scared to ride trains because they couldn't stop, but these air brakes gave people the confidence that they could ride the train safely. However, on freight trains, it took a lot longer for these air brakes to be adopted. And there was this person named Coffin who was a big advocate for mandating these air brakes be used on all trains. And he worked for the Iowa Railroad Commission. And when he started, he said that the people on the commission just kind of thought that this was the way it was. Trains were dangerous and brakemen were going to die, so there wasn't really much we could do about it. This is just how things were. But Coffin kept getting all these reports about brakemen being killed and was like, no, these are all the same cause. We have to do something about this. So he did a lot of advocacy. There's transcripts of a Senate hearing from the Interstate Commerce Committee that I just find riveting. I'm like reading these Senate transcripts from 1890, and they're amazing. Coffin had a lot to say in favor of mandating the air brakes on all trains. The industry people didn't want to be regulated, so they had a lot of interesting arguments. They didn't want to pay to add these air brakes to all their trains. They thought that brakemen were kind of expendable and cheaper, which is terrible. They were like, the air brakes are still going to fail sometimes. It doesn't matter that handbrakes fail. The air brakes are also going to fail, so why should we switch? They simultaneously made two arguments. They said, we are already innovating without legislation. We are testing new things all the time to improve the safety on the train. If you regulate that there's some minimum standard, we're going to adopt the thing that'll meet the law, and we're going to stop innovating. So that was one argument. In like the next breath, this guy at delivering testimony said, and what if something better comes along and we've already have all this sunk costs into these air brakes? It's like, wait a second. Are you saying you're going to keep innovating, or are you saying you're going to stop innovating? Because now you're saying both are going to happen. They really just didn't want to be regulated. They said they have other maintenance they have to pay for. They can't possibly afford these. They said you should have regulated this 25 or 30 years ago. All sorts of things. My favorite objection from the president of the Pennsylvania Railroad Company was, you're going to regulate the trains? What's next? Are you going to regulate the bridges? It's like, yes, please. We want the bridges to be safe too, actually. So yeah, it turns out that the US Railroad Safety Appliance Act passed Congress in 1893, mandated the use of air brakes and standard couplers to connect the trains together. In 1900, it was fully enforced, and all trains, whether passenger or freight, had to be using these safety devices. And accidents and deaths of both people and things being run into by trains and brakemen operating the trains went way down. This helped a whole lot. It wasn't perfect, but it was way better. Okay, that was your railroad history lesson. So now we're going to talk a little bit about C. So why might companies choose C? Who works at a company who has C code in production today? Okay, yeah, good, all right. You probably have a variety of reasons why you're doing that. It's a proven solution that has worked for 40 years. It's fast. It has very little overhead. It's kind of close to the machine, close to the assembly language. It uses very little resources. There's a C compiler to target just about any sort of platform you might want to run on. The language is simple. There's not a whole lot of syntax to learn. I would argue that it's a little bit deceptively simple because there's a lot of interesting things that C code can do. You might have a lot of existing C code, or you might want to interface with existing C code. That makes it easy, means using C would make that easier. And C doesn't really change a whole lot. In enterprise software, the field moves rather slowly, and you don't want to have lots of parts changing out from underneath you and having your code become obsolete. So, but in order to get all these advantages, you have to agree to what I see as a huge disadvantage that outweighs all of that, is that C has all these memory safety problems. It's not memory safe. These problems include use after free, double free, memory leaks, buffer overreads and overwrites, null pointers, data erases. Oh my, this is just a lot of problems that you have to sign on to when you are shipping C in production. And I'm sure those of you who have C in production can tell lots of stories about problems caused by all of these. And a lot of people say, well, if you just be more careful, then we can avoid these problems. It's not a matter of being more careful. The experience in the past 40 years has shown we're not capable of being careful enough. There is a vulnerability called stage fright in Android, and this blog post was illustrating some C code to try and explain what the root cause of stage fright was. And he said you'd have to be more careful than the entirety of the Android security team. Every C developer shipping code in production has to be more careful than that. There was a great presentation and a post about Microsoft did some studying of the problems that they had to issue security updates for. Over the last 12 years, about 70% of them were due to memory safety problems. You'd have to be more careful than the Microsoft security team. There have been some efforts to make C safer. There are tools like Valgrind, there's tools like address sanitizer, undefined behavior sanitizers. I found this tool called ICOS that does abstract interpretation as a static analysis. It's from NASA. So NASA has a really rigorous engineering discipline. So if that's the kind of investment you want to make, you can check out tools like that. There are the MISRA guidelines. All of these kind of strike me as things you do after the fact. You write the code first, and then you try and make it safe, which you have to make sure you do those things. You can't ever forget. You have to build them in the processes. You have to allocate time to do that and fix the problems you find. It seems like kind of patching it after the fact. There are some varieties of C people are creating. None of these have really caught on much. You're still writing C that has very little abstractions. You have to reinvent the wheel all the time. You don't have modern tools that go with it. And if you're going to be switching languages anyway, I'd advocate that you look at all your options. And of course, there's C++, which improves some things, but not everything. There's still a lot of undefined behavior. There's still a lot of pointer problems you can get into. Multi-threaded programming is still a big problem in C++. So what can we do about this? And that brings us to the Rust part. So Rust is a language out of Mozilla Research. It's trying to learn from the mistakes of C and bring in ideas from a bunch of other languages I see it as moving our industry forward and trying not to repeat the same mistakes over and over again. I have 5 reasons why I think Rust is ready to last as long as C has. The first reason is that it fixes these memory safety problems. It's an improvement upon the status quo. It does this through a system of ownership and borrowing. And I'm going to show some examples of how this works. This is some Rust code. It's a main function that creates a string on the heap that we can grow and change in size. The owner of that memory is this variable x. And when that owner goes out of scope, that's when the heap memory gets cleaned up automatically. Rust kind of looks at this code as it's compiling, inserts a statement at compile time that at the end of main that cleans up that memory. So we don't have to write free the memory, the X, manually. But there's also not a garbage collector running at runtime. This is all at compile time. This is another example. In this example, we've got the same string in X. Then we say let Y equals to X, and we try to print out X. This line here moves ownership of the string from X to Y. And this code does not compile because we're trying to use X again after we've moved it into Y. So this data still only has one owner. After that point, we've moved it into Y. Y will clean that up, and X is no longer valid, and we're no longer allowed to use it after we've moved it. So we don't have double free problems, and we can't use after free. This code, instead of moving ownership, this borrows, Y is an immutable borrow of X. It's allowed to read the data that X owns, but X is still responsible for cleaning up the memory at the end of the function. And this code compiles, and we're allowed to read using either X or Y. In this example, we are trying to create a dangling pointer. We have an inner scope, and we're trying to return a reference to heap data from that inner scope. The problem is that the way Rust ownership works, X is going to get cleaned up at the end of that inner scope. So this code doesn't compile because we're trying to use the reference after that data has been cleaned up, and Rust can see that at compile time and doesn't let us run this code because X gets cleaned up. Rust has a lot of other safety mechanisms that I don't have time to get into fully. One of the rules about references is that you can have either one mutable, changeable reference at a time, or you can have many immutable references for reading at one time. So this prevents data races so that you can't change a value while someone else is trying to read it. There are no pointers there's the option type that represents either something holds a value or there's none, the none value, and the compiler makes sure you handle both some or none at compile time. Out of bounds array accesses or data structure accesses, at runtime, it just stops the program immediately and doesn't let you continue with invalid data that isn't part of your data structure. The ownership rules apply across multiple threads. There's parts of the type system that allow you to express transferring ownership or borrowing across multiple threads. So now programming parallel or concurrent programs is checked at compile time, that you don't have data races across threads. Jessica this morning said a neat word that I hadn't heard before, which is the person byte. It's what you can keep in your head all at one time. And trying to keep all these rules and make sure you're doing all these things right in your head with C is really tedious, and as we've seen, is error prone. It's too much for one person to hold in your head, in addition to your problem domain. But there's someone who's really good at keeping track of tedious things and making sure that they're right every single time. It's our computers. So I see Rust as making the computer take care of all that tedious tracking of whether the memory accesses are right or not. And I can forget about that. The compiler's going to tell me when I get it wrong and I have to go fix it, yeah. But if my code compiles, I don't have to worry that I've missed someplace. And I can just concentrate on my domain. And this is the second reason I think Rust is going to continue to grow and to last for the next 40 years, is that this makes low-level systems programming code something that everyone is capable of doing, not people who have extremely large person byte capabilities to hold all this memory access in their head as well as the domain, which I'm not sure that anyone actually exists because of the problems we see, but more people can program safe systems level code with Rust. I do have a caveat. There is an escape hatch. It's the unsafe keyword. It lets you opt out of not all of Rust safety checks. It lets you do a few very specific things. And by putting unsafe around some of your code, you're saying, OK, compiler, I understand that you can't ensure that this code is going to be safe every single time. I, as a person, am going to audit this specific code, and I will make sure that I'm following the memory rules. And this is useful in certain performance cases when you're trying to express certain pointer arithmetic, when you're trying to call to external code that the compiler can't possibly know anything about. And as long as you don't put your entire program in an unsafe block, what I like about this is that if you have a site fault or a memory access problem at runtime, you know it came from one of those unsafe blocks. It's like, hey, look over here. This is probably where the memory problem came from because the compiler didn't check this part. So you've lessened the places you have to look to debug to figure out those problems. I also think that this unsafe keyword doesn't invalidate things because this is opting out of the safety checks rather than opting into them. So as opposed to the sanitizers that you have to remember to run after all the changes to your code, this is the default is to write safe code, and you can opt out of it if you need to. If you want more information on writing unsafe code, there's this great talk for building an unsafe foundation. The other neat thing is you can build safe abstractions out of unsafe code. And there's a whole book on unsafe code called The Rustonomicon. Like air brakes sometimes don't stop a train, Rust doesn't prevent all problems you might have with software. It does not prevent you from having logic bugs. it can't tell that you meant to tell the program to do one thing and it's actually doing another. So you still need things like tests, and you still need to write things like fuzzers. But by choosing to use Rust, you're getting memory safety. You're not going to have all those problems that C has. So let's go back through the reasons that you might choose C and see what we're trading off, because there's always trade-offs in any sort of decision you might make. Performance, Rust is on the order of C's performance. There aren't, the additional checks that Rust does are mostly at compile time. There isn't a garbage collector. It isn't checking much at runtime. You can still get, we have the goal of having zero cost abstractions, which means that the abstractions you use are compiled down to code that you could not write better by hand. Of course, there are always things we can improve on, but zero cost abstractions are what we're aiming for. We're hoping that Rust will perform as well as C in the situations you want to use it. Portability, Rust compiles to LLVM intermediate representation, so you can write Rust and compile it for any platform that LLVM can. There are C compilers that target platforms that LLVM doesn't. There could be a non-LLVM backend for Rust. There isn't one yet. There isn't a reason why there couldn't be other than people putting in the work. So if you need to write code for one of the platforms that Rust doesn't support, that could be a deal breaker for you. But we do support a lot of platforms. So this one is a little bit of both. The big downside is Rust is more complex. And we are trying all the time to lessen the learning curve through books and video courses and various learning materials. There's definitely more features and syntax than C, but we're trying to express complex ideas such that the compiler can understand them, and that does take more syntax and more complexity to express. If you have legacy code, a neat thing is that you can write extern functions that let you call C from Rust and Rust from C. And a lot of languages also have a way to interface with C, so you can use that to, say, call Rust from Python or call Ruby from Rust. I actually have a whole talk on porting a library, the Zopfli compression library that was written in C, porting it to Rust function by function, keeping it compiling and passing tests at every commit. And the thing I like about this technique is that you don't even have to finish. You don't have to convert the whole thing to Rust to see benefit. You could convert just the parts that change the most, the parts that have the most bugs, and you could set it aside for a while if you have other high priority things to work on, but you still get those benefits along the way of converting little pieces to Rust. So you don't have to rewrite all of your stuff in Rust to see benefits. Stability is one I want to spend a little more time on. There is a new version of Rust that comes out every 6 weeks. We have a train release model, sort of like Firefox and Chrome do. So you might think that Rust is really unstable and it's going to change all the time. But we have really strong backwards compatibility guarantees we've committed to. Rust 1.0 came out in May 2015. So we've been stable and shipping stable codes every 6 weeks since then. We do have a little bit of an out we've given ourselves. We reserve the right to fix compiler bugs, patch safety holes, and change type inference in ways that occasionally require new type annotations. We do not expect any of these changes to cause headaches when upgrading Rust. So we can fix our own bugs. In practice, what this has meant, we run a survey every year. In the 2018 survey, we had a question that said, has upgrading broken your code? And 92.6% of people have said, no, it has not broken your code. This question, I feel like we need to change the wording of it a little bit because it doesn't really distinguish between breaking compilation, which is what our stability guarantees are really about, versus breaking runtime behavior or slowing down your code at runtime or speeding it up. broken it in that way. And I'd like to be able to dig into those problems a little bit more and see how we're really doing on our compile time stability guarantees. Another part that I think, part of our stability story that will let us last for 40 years is that we have a goal of stability without stagnation. We want to be able to evolve Rust to learn from our own mistakes, to make the language easier to use and to learn, while still not breaking our backwards compatibility guarantees. And the mechanism that we've designed to use in Rust is called additions. And this is a link to a detailed specification of what additions are. I'm going to go over the high-level idea. Mainly, they are opt-in. About every 3 years is what we're thinking. We've just made Rust 2018 edition, and the original edition of Rust is 2015. So we have 2 editions right now. What they are is the biggest change we want to make that's not backwards compatible is adding new keywords for adding new features. So for instance, we're going to be adding asynchronous functions to Rust, the language, soon, and we wanted the async keyword to be able to do that. But your existing code might have function async. So if we added that as a keyword, your function would no longer be a valid Rust function. So we added this idea of additions so that if you opt into treating your code as Rust 2018 edition code, then async would be a keyword. But if you did nothing to your code, upgraded your compiler, it would still treat it as Rust 2015 edition code, and it would continue to treat async as not a keyword and continue to compile your code. When I first heard of this idea, I thought it sounded terrible from a compiler maintenance point of view. You'd have to maintain 2 ways to use every feature forever because we wanted to commit to all additions being supported forever. But it's actually not that bad. The way the compiler works today is you have your Rust source code. The compiler turns it into high-level intermediate representation, and then turns it into mid-level intermediate representation, then turns it into LLVM intermediate representation, and LLVM turns it into machine code. A lot of the complex analysis that the compiler does, such as borrow checking, optimizations, and code generation, happen at this mid-level intermediate representation level. The way additions have been implemented is that they're kind of at the surface level. They affect the source code that you'll write, and they affect the high-level intermediate representation. But once you get to the mid-level representation, the mid-level stuff is all the same, no matter which edition you came from. So all this complex analysis code can stay the same for both editions, and it's only the first part of this conversion that is a maintenance burden. Because the compiler understands both editions and multiple editions once we have more, and can compile 2015 code or 2018 code, that means we're not going to have an ecosystem split. Rust 2015 project can depend on a project written using Rust 2018 idioms, and vice versa. So it doesn't matter if all your dependencies have opted in or not. The same compiler can understand either code and can compile it all together. And the important things about this is that you get to pick when you decide to change which edition you want to use. You can keep upgrading your compiler every 6 weeks, but you don't have to switch on that flag to change the idioms until you decide the benefits outweigh the cost of upgrading. And never is a totally valid choice. We plan to support Rust 2015 edition code for as long as Rust exists. In order to decrease the burden of switching editions, we also have a tool called RustFix that for as many changes that we can do automatically, it will apply those changes and fix up your code and move you to the new edition automatically. So we're trying to, if you do want to switch to the new edition, we're trying to make that as painless as possible also. The editions concept, I am confident that with using this to evolve the language means we're never going to have a Rust 2.0. We're not going to break backwards compatibility. So we hope to be as stable as C is for the next 4 years. We do have a lot of things that aren't done yet with Rust that might prevent you from using it in your company. We don't have a standard. It's going to take a long time and a lot of work. We do want to get there someday, but it was years and years before C has a standard, so we do want to get there, but we're not there yet. We don't have a certified compiler. That will matter in some industries. We do want to have a long-term support release that gets things like security fixes and certain bug fixes. We don't have a policy for that yet. Cargo is the build tool that Rust kind of expects you to use. If you don't use that, it gets a little hard to tinker with. And some companies have build systems that everything needs to feed into, and we have work to do to make Cargo fit into build systems better. We have an open source package registry for open source code. We don't have good solutions for libraries that you might want to keep private, only share within your company. And the ecosystem is still growing. So there might not be a library for everything you might want to do in Rust yet. But these are all things we're working on, and we hope to get there soon. Another reason I think we're going to last is that there are today a number of large enterprise software companies using Rust, and they've invested their products in Rust, so they're invested in Rust's future. The biggest one, of course, is Mozilla. If you heard of the Firefox Quantum release a while ago, where Firefox got a lot faster, one big reason of that was a big component that was rewritten in Rust was shipped with that. The component was the CSS rendering that can now render all the CSS properties in your page in parallel. And they did some analysis of the security bugs in this component that was written in C++ and found that since the beginning of Firefox, there were 69 security bugs in this CSS component. If they could have gone back in time and written in Rust from the beginning, Rust would have prevented 51 of those, which is about 3/4 of them. So I think that's a pretty good improvement on the security and of this Firefox component, and the speed increase too. If you know Patio11 on Twitter, Patrick McKenzie, he has this word he likes to say, "Apamagubooksoft," and it represents a number of big software companies. Apple, I don't know of any public uses of Rust at Apple. They have Swift, which actually is really similar to Rust. I was in the Swift talk earlier, and they have a lot of the same problems and a lot of trying to solve the same problems that Rust is, but use different words for it. So I was like sitting there trying to translate. I'm like, they're hitting the same problems that we are. They're really similar, and there is cross-pollination there. So I hope there's more in the future, and we can both learn from each other. Amazon is the AMA part of this, and they recently announced their Firecracker micro VM. Google is also kind of secretive. They have this Fuchsia operating system project that they haven't really said what it's for yet, but the code for it is like on the internet and open source, and there's parts of it in Rust. Facebook has the Mononoke Mercurial server to manage their huge Mercurial monorepo that the canonical implementation of Mercurial couldn't handle fast enough. And Microsoft announced they have this IoT Edge platform that does analytics like on IoT devices and then sends the results to server. So that's AppM and Gubooksoft. We've got 4 out of 5 of those using Rust publicly. The 5th reason that I think we're set up to last is our project's governance. Like the trains, the adoption of this is not only for the technical reasons, there's also political reasons. And I think we are building a good foundation here. We don't have a BDFL, a benevolent dictator for life. There's not just one person making final decisions on Rust. We have a number of teams and working groups made up of multiple people responsible for different parts of the language. And we have a lot of different people represented on those teams and working groups. We have programming language theorists, people with PhDs in programming languages. We have people using Rust for a product for a company. We have people using Rust for fun. We have people who come from the low-level languages like C and C++. We have people from high-level languages, like I come from Ruby, and in our surveys, Python is consistently the #1 language that people come to Rust from. And there's people from functional languages like Haskell that bring a lot of the functional influence into Rust. And our big decisions are made in public by a system of requests for comments, proposals that everyone can see, and the teams responsible for making the final decision state their reasoning in public on these RFCs. So while we might not make a decision on something in the exact way you might want, our hope is that you'll at least understand why we're making those decisions and feel like we have heard your point of view. I feel really strongly that as an open source person that this is important, that this isn't driven, Rust's direction is not driven by a corporate closed entity making decisions in secret that you have no idea why they're doing, and we're not going to take it in some surprising direction. If we do, take it in a different direction, you'll know that we're doing it. You'll be able to see us do that. Another big part of our governance is that we have a code of conduct and have since the language was open sourced. And I love that this has been since the beginning, so we don't have to have the argument about whether we should adopt one or not. That decision has already been made. We have one. We are trying to make a professional space for professionals to work on technology without problems. We're not perfect, but we are acknowledging that there are problems that we need to be handling to make Rust a welcoming place for everyone. So just to sum up, these are my 5 reasons why I think Rust is going to be able to last the next 40 years. And now we're going to talk a little bit more about the railroad industry and how that relates to what we're doing today. The software industry has a reputation for being a little bit arrogant. We think we can do things better than other fields have done them. There's the time that a software company thought they could do juice better than other people and actually didn't work any better than squeezing juice packet by hand. There was the time that Lyft reinvented the bus. And there was the time that there were people stuck in a cave and Elon Musk thought he could do cave rescues better than the people who specialize in that sort of thing. So we think we're better than other industries. If you just add a little software, we can totally fix these long-standing problems that other industries have had. We're so much better. I think we have to work to prove it. If we actually are better, we need to show that we're better. And we might need regulation to do this, but there's a problem, is that it's pretty easy for everyone to understand that if you can't stop a train, people are going to get hurt. People are going to get killed. Pretty easy to understand that being on top of a moving train in any weather is a dangerous thing. But it's not easy to understand what memory on safety even is, and it's not even easy for us to see what the effects of that are. So, like, I'm trying to imagine the Senate transcript from reading that in the future from now of software people trying to explain memory unsafety to senators, and it's terrible. I don't see this going well. So I don't think government is going to improve the safety of software. But I think we can improve ourselves. We can be our own informed consumers that demand that our dependencies are safer before we incorporate them into our software, because we understand our own problems. That is the part that we can show that we're better. The railroad industry got really started in 1830. Westinghouse invented the air brake in 1869, and then everyone was using it by 1900. So this is about 80 years. No, that's not right. 70 years. About 40 years to invent a safer thing, about 30 years for people to start using it. Rust became stable in 2015. I'm arguing that that is a better, safer C. I don't know how long it's going to take us to adopt something that's memory safe. Can we do better than the railroad industry? I don't know. I want us to be better. I'm not sure if we are better. I hope that we're better. All right, that's most of my arguments. If you're still feeling a little skeptical, that's totally fine. I'm willing to be wrong. I am willing for Rust to not be the solution, as long as we do something. Let's just do something to fix these memory safety problems that keep happening over and over and over again. Maybe it's not going to be Rust. Maybe there's something better than Rust. Maybe it's Zig. Go to the next talk. I'm looking forward to it. Maybe it's Go. There's a Go talk tomorrow. Or maybe it's all of them. Maybe there's not going to be one replacement. Maybe there's different replacements that are better for different situations. That's fine. I'm totally okay with that. You don't have to choose Rust. I just want us to stop making the same mistakes over and over again. Let's make some new mistakes. Okay, again, this is the link to my slides and links that I referenced. I'm Carol's 10 cents. There's a code for everyone to have that will get you 40% off anything at manning.com, and that code is right there. And I would like to thank my test audience, my daughter Vivian, and my cat Baby. They were very patient and provide valuable feedback. Okay, let's see what questions we have. Let me stop mirroring here. Or start mirroring, rather. Okay, where are my questions? Okay, let's see which ones I like best. Okay, let's do what's with the name Rust. There's multiple stories here. The people who started Rust enjoyed riding bicycles, and bicycles often have to deal with rust. Our logo is kind of a bicycle gear. There's also a fungus called rust that grows on wheat sometimes. That is a potential an inspiration that has been suggested as why rust. I like to think of it as something stable, something that has been around a long time, a stable, strong coating on the outside. There's actually this Corten steel. The U.S. Steel Tower in Pittsburgh is built out of it. It's steel that is meant to rust on purpose to protect it instead of paint. So I like thinking of Corten steel. Partha, I liked your question. If you are still here, I have an envelope for you. There you go. Thank you. OK, why would you recommend Rust over Go? I also like this question. So Anonymous, who asked this, if you would make your way to the front while I'm answering. There are a couple big differences with Rust and Go. They're actually aiming for slightly different spaces. I think they get compared a lot because they came out around the same time, and they're both aiming to be kind of C++ alternatives. Go has a garbage collector, which might be a deal breaker in your application. So if you can't have something at runtime using resources, then I would recommend Rust. If you're trying to interface with Google products, I think Go is probably going to be a really smooth way to have everything all in the same language for simplicity purposes. Yeah. I think you should check them both out, and you should I think one of them is going to resonate with you over the other. So I think you should do some intro programming in both of them and make your own choice. So is someone going to fess up to asking that question for a free code? No? OK. All right. Arguably, one of the reasons for choosing C these days is great IDE support. Does Rust have solid IDE integration? We're working on it. This is another one of those things that we know we need to do better at. There's this thing called the language server protocol that is trying to standardize the way that languages can talk to IDEs and tell the IDE things about the code. And we have an implementation that does code completion, inline errors, jump to definition. And VS Code has the best maintained plugin that uses the language server protocol. IntelliJ also has pretty good Rust support. So I did Ruby before Rust, and I love the book Working Effectively with Legacy Code by Michael Feathers. But in that book, he talks a lot about leaning on your tools, using your IDE, using automatic refactorings. And in Ruby, because of all the metaprogramming, and you can take a string and run it as a function, and you can't use some of those tools because you can't be sure that you've caught everywhere that function is called, because it might be called dynamically from something. So I had a lot of jealousy for IDE tools while I was writing Ruby, and I'm looking forward to the days that we have those tools for Rust. They're not there yet, but they're more possible to make than they are in Ruby. So does anyone want to claim that question? Thank you very much. OK, let's see what other question I like. Latest question. That's a pretty good question. Oh, OK. This is a good question. Mentioned a new async in 2018 edition, and is async already in the 2015 edition? It's actually in neither edition right now. When we created the 2018 edition, we just reserved the keyword for async, and we wanted to have async support done by the time we shipped the edition, but it's not done. People are working on it right now. There's a lot of open discussion on the RFCs about the exact syntax, the exact way it's going to work. So if you're interested, you can go check that out. But it's not in either. And once it is done, it will probably be available in both. It's just that the syntax in Rust 2015 is not going to use a keyword, so it's not going to be as nice as syntax as it will be in Rust 2018. So who asked the async question? All right, then that is all the codes I have, and I think I am just about out of time. So thank you very much for having me.